This is Free Range Digital Design Foundation Modeling, Chapter 5, first video. So we still haven't done any digital design yet. We are still working on background information, and in this chapter that includes various number conversions and just general manipulation with numbers. Also, we'll get into some useful codes. This is our form of a number that we're going to work with. We presented this in a previous chapter. Numbers here have integral parts and fractional parts, and it's divided, separated by this dot, which is the radix point. So these A values are the individual digits, the symbols in the ordered set associated with that number system. And what we're interested in particularly is subscripts on these digits. So these subscripts are actually going to be associated with the weightings associated with each digit. So the weighting associated with each digit is the radix to the power of that subscript. So we'll see a couple examples here. So let's do this. So this is 3 examples of various numbers that we're going to convert to decimal. I'm going to list the weights on these. 8 to the 0. This happens to be a base 8 number. 8 to the 1, 8 to the 2. Notice that these subscripts follow these subscripts up in this example. So the final answer to this thing, 3 times 8 to the second power plus 2 times 8 to the first power plus 7 times 8 to the 0 power plus 5 times 8 to the minus 1. The second example here looks like binary, but there's no base listed there, so this is interpreted as a decimal number, and this is it's already in decimal, so no conversion necessary. So it's really important to always use a base on your numbers. If you don't, it's going to be interpreted as decimal. Third example here, we got 10101.11, 2 to the minus 1, 2 to the minus 2, 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. So the answer is going to be 2 to the fourth plus 2 to the squared plus 2 to the 0 plus 2 to the minus 1 plus 2 to the minus 2. This is actually very doable. So this could be 16 plus 4 plus 1 plus 1/2 plus 1/4 equals 21.75 if you want to do this. So this final example here, we got a hexadecimal, so F3A.34. This is going to be, I'll list the radix is up here, squared, 61, 16 to the 0, 16 minus 1, 16 minus 2. So this is going to be, our decimal equivalent at F is 15 times 16 squared plus 3 times 16 to the first plus A, the decimal equivalent is 10, so it's 10 times 16 to the 0 plus 3 times 16 to the minus 1 plus 4 times 16 to the minus 2. Next set of conversions is converting between binary and hexadecimal. Now, computers only understand binary, but the problem is when you list a whole bunch of bits, which is binary digits, which is base 2, you don't want to list too many. It gets too hard to read, so you switch to hexadecimal. Okay, and you'll see how much that saves in this example here. So once again, anytime you have to list over 4 bits, switch to hexadecimal. So the group of 4s is just a matter of dividing these numbers up into groups of 4. I'll just do this real short here to take the shortcut here. Now I've successfully divided that in groups of 4s, and I just have to read off this thing what the value is. So I bit stuff 2 zeros on there, which makes it 4 bits, doesn't change the value of the number. So this first number here, leftmost 4 bits is 3. Next, this is a 2. This is an A. 1010 is associated with A hexadecimal, and then bring down the decimal point. 1001 is 9. Okay, so I've successfully converted that to hexadecimal. I'm going to for sure the radix listed after it. So this example is a little bit different. 10111101.1. It's tempting to say, oh, that's a 1, but it's not actually a 1 according to groups of 4. I have to group these into 4, and once I add the zeros onto that, that becomes an 8. If I listed it as a 1, associated number would be 0001, which is not what that is. So the second group of 4 is this one and this one, and we'll stuff some zeros in the front. So this the equivalent here is 1, 7. This is a 7. 1, 7. 1101 is a D. D. 0.8, and I'm going to for sure put that radix on it. So the group of 4s works in both directions. The other direction here is going from hexadecimal to binary. So F 7A B 0.34, and what I'm going to do is just write groups of 4 for each of these hexadecimal digits, and it's going to be 0100 0011, bring down the decimal point. B is 1011, A is 1010, 7 is 0111, and F is 1111. Okay, so once again, this is the F, this is 7, A, B, 3, and 4. Dead beef is a common word you see in digital design. It's sort of clever because it spells out words using hexadecimal symbols. D is, just write this out, D is 1101, E is 1110, A is 1010, and D is once again 1101. Okay, so I have these memorized. You can memorize them, what you should do, read them off the table, generate the table yourself if you need to, but best idea is to simply memorize these. B is 1011, E is 1110, 1110, and F is 1111. And don't forget the radix point, like I did on that example. Oftentimes we need to multiply and divide numbers by powers of the radix, and once we do that it becomes really easy, and you've done this a million times in decimal, whereas divide a number by 10 or multiply a number by 10, you move the decimal point to the left or right. It's really easy, as you know, to divide by powers of the radix. You've done it a whole bunch of times before. For example, here 1000 equals 10 to the cubed, and so that means if I'm dividing this number by 10, I'm going to move this decimal point 3 places to the right, and there's my answer. Same with this example here. I'm going to move the decimal point 3 to the right, and I'll write this out 0.1334. Multiplying a number by a power of the radix, 100 equals 10 squared, so that means I'm going to shift that decimal point 2 places to the right, so which means add 2 zeros to this one. For this one, I'm going to shift it once and add a 0, so we'll write this out 9030. So you've done that a lot of times, you've seen that many times before, but it works for other radixes too. And so let's do a couple examples here. So 256 equals 16 squared. Notice that the radix for these examples is 16. And so 256, I'm dividing these. 256 equals 16 squared. So what I'm going to do is shift that radix point 2 places to the left. So this is going to be shifting it right there. I'll put a decimal point in there. There's your answer. And shifting this 2 places to the right. 0.0f34, and this is base 16. The second example here is divide the following number by 64. It's actually given in an octal, which is base 8. 64 equals 8 squared, so that means I'm going to shift that decimal point 2 places to the left. So this equals 234 base 8. Okay, divide the following numbers by 32. 32 equals 2 to the 5th. So that means I'm going to shift that decimal point 5 places to the left. Let's just do it. 1, 2, 3, 4, 5. Looks good. Same with this example. 1, 2, 3, 4, 5. Better write that one out. 0.00101 base 2. Really useful trick to know. It works with multiplying 2. So here's some hexadecimal numbers. 256. equals 16 squared. So that means if I'm multiplying these, I'm going to shift this 2 places to the right. So this is going to be C4A7. Stuff 2 zeros on it, and there's my radix point. Same idea here, shift it 2 to the right. E77 is E77. I shift that 2 to the right. Here's my answer. Throw in a radix point. Okay, so 512. What is that? 512 happens to be 8 cubed, so that means I am going to multiply this by, well, I'm going to shift the radix point 3 places to the right, so it's 217, 2117, 000. There's my final answer. It is base 8, so I need to toss that in there. And same with these guys. Okay, so the following number, I multiply the following numbers by 8. 8 equals 2 to the third. So what I'm going to do is is add 3 zeros if I need to, or just shift that decimal point 3 places to the right. So this is 1 0 0 1 1 0 1 0 1, and I need to add 3 zeros to this thing, and there's my answer. 1 0 1 0 1.1. Just put some zeros on this thing. Multiplying this by, I have to shift that radix point 3 places to the right, so it's 1 2 1 2 3. Okay, and there's my final answer, base 2. So we'll write that out. 1 0 1 1 0 0 point. We'll just leave it at that. 2.